Good morning to Doctor. We are from SSCM1533, Logic and Set Theory, Section 01, Group 11. My name is Teo Jasin. We are now presenting for our group project with the titles Quantifies Orders and its Effect. There are five parts for our presentation today, and the first part is the introductions of universal quantifiers. The second part is the key definition and notation. The third part is the mathematical proof. The fourth part is the real life example, and the final part is the discussions and conclusions. There are two fundamental quantifiers, which is universal quantifiers and existential quantifiers. Look at the first one, which is universal quantifiers. It has a symbol of upside down capital A, and it means for all or for every. Look for the example in the slide. For all x px means px hold every element x in the domains. In a simple word, if all x px is true, means every x inside the condition px should be true. Moving to the next one, existential quantifiers. It has a rotate sans serif capital E as a symbol, which means there exists or some. For example, there exists x px, which means px hold at least one x in the domain. In a simple word, if there exists x px is true, which means there must have one or more than one x is true in the condition of px. Moving to the next, let's talk about how we read the structure of quantifier expressions. Specifically, we will look at notation, scope, and bindings. To make sense of these three rules, let's analyze the mathematical statements at the top of the slide. All x exists y, x plus y is greater than 0. First, let's address scope, which you can see in the middle of column. The scope is simply the domain of inference, the exact part of the formula which the quantifiers operate. It usually indicates by brackets, or we can say that it is the conditions of statement which quantifier apply to. This brings us to binding. When a variable is for inside the scope of quantifiers, we said that the quantifiers bind that variable. Binding completely changes the nature of the variable. It is no longer a wildcard. Instead, it now has a strictly defined range of value. Rather, that means every single element in our universal, or at least one specific element. Finally, we distinguish between free versus bound variable. A variable is considered bound if there is a quantifier applied on them. In our example here, both x and y are bound because each of them have their corresponding quantifiers. If we add another variable z inside the bracket without adding a quantifier for it, z will be said to be a free variable. Free variables do not have their conditions defined inside the formula, so their value must be assigned from outside of content before we determine if the statement is true or false. Understanding this boundary ensures us to interpret complex logical framework accurately without losing track of what our variable actually represent. Moving to the next, the questions of orders. As you can see in the statement, O x O y pxy is equals to O y O x pxy. In the natural language form, it means for every number of x and every number of y, there is scope, and for the another one is for every number y and every number z, there is the scope. Each bring the same meanings if we exchange the order of quantifiers for all x and all y. And the statement B, which is at this x, at this y, pxy, is actually also same with at this y, at this x, pxy. In the natural language form, it is said to be there exists a number of x and exists a y, there is the scope, and there is a number of y and exists of x, there is the scope. So it also brings the same meaning with we change the orders of exist x and exist y. So a simple conclusion that we can make here is if we using two same quantifiers, if we exchange their orders, it doesn't affect their meanings. However, it is different when we using two different quantifiers. Look at the statement C. For all x, there exists y. when x is less than y, which means every number of x that exists a number of x is less than y. And the another statement will exchange the order of exists y and all x. Its meaning becomes there exists a number y that is greater than every number x. So if we exchange this, we can clearly see that it brings a different meanings. And we also can see that statement C is actually a weaker statement than statement D. Next, I will pass the sections to mathematical proving to my teammates.
Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Zrisha Muhammad Junaidi. Uh, Today I want to explain about mathematical proof, proving the difference from argument. The theorem is in the domain of real number, all x some y where x less than y is true, but some y all x where x less than y is false. The proof of statement A, all x some y where x less than y is true. Uh, let's go to the example. Let x be the element of real number be arbitrary. We can choose. Let's choose y equals to x plus 1. Then y is element of real number and x less than x plus 1 equals to y. Since x was arbitrary, all x some y where x less than y whole. Hmm, for statement B is false. Suppose some y of for element of real numbers such that all x for element of real number where x less than y. So let x naught equals to y plus 1, then x naught is a real number, but x naught equals to y plus 1 bigger than y. This contradicts the x naught less than y. So it's a contradiction. So the statement B is false. Another one is visual institution, the order of choice. Key inside outer qualifier equals to fix first. Inner quantifier is equals to respond to outer choice. The first one, game is adversary, pick any x. You respond, so we can pick y equals to x plus 1. You always win. Strategy adapts to x. So the statement is true. Then another one is you must commit to y first. Pick x equals to y plus 1. So the adversary always win. You can adapt. The statement is false. This is the real life example. For police and law, all person, some lawyer. People can get help. Every person can find a lawyer, but the problematic is where the some is first. What, for example, some lawyer, all person, lawyer helps them. One lawyer handles all people. So it is impossible for one lawyer to handle all of the people. For medicine, each patient has dose that works. So all patient, not all, some dose. For the problematic is not all dose can work. One dose works for all patient. Not not all the dose can work for all patient. Some patient cannot accept that dose. So that's all. Thank you.
Hi everyone, let me introduce myself. My name is Nurul Ain bin Zulkifli. I will present for conclusion section. We can see that the order of quantifiers is not just a matter of changing sentence style, but it can actually change the meaning of statement. First, order is meaning. When we switch the position of quantifiers, such as for all and there exists, we are not simply rewriting the sentence. The logical meaning can become completely different. For example, for every person, okay, there exists a solution is different from there exists a solution for every person. The first one means each person may have their own solution, while the second suggests that is one solution that works for everyone. Second, the outer quantifier is the one that is chosen first. The inner quantifier depends on the first choice. We can think of it like a game choice. The first player make a decision. So changing the order change the world structure. Okay, third, this has real consequences in real life. Quantifier ambiguity can affect how we understand things like contracts, policies, medical rules, or cybersecurity requirements. A small difference in wording can change who is responsible or what condition needs to be satisfied. Lastly, quantifying order is also important in mathematics. The epsilon delta definition in calculus depends on the correct order of quantifiers. If order is wrong, the mathematical statement can become false. So, in conclusion, quantifier order is control meaning. This leads us to the question, can we find a real world contract or policy while changing the order of condition, change in interpretation? Okay, only that for me. Thank you everyone.